Welcome to another video explaining the universe using the particle model. Well, today's video is in response to questions from a viewer. I try to do that, especially when the viewer seems quite interested in the model. So if you happen to have a question and want to ask Particle your questions, you can do that at the website under notifications. His initial comment to me was this. He says, I've been watching all your videos the past couple of months. Almost finished them all and have a few questions about your interesting model. Well, that's quite nice. You don't get a chance to hear that about viewers, whether someone has really picked up an interest in it that way. So thank you for your interest, and I hope my answers help. Some of my answers may provide an opposing view which are meant to clarify, not to criticize. Okay, this is his first question. He asks, does your model assume a fundamental solidity of particles at the lowest level, for example, G3 or lower? Here I'm using solidity not to describe a state of matter, but rather to describe the near 100% elasticity of collisions between particles. For instance, when one goes swimming, you don't actually enter the water, but you rather push the water atoms apart to make space for your body. This is the type of solidity I am asking about. All atoms, whether frozen, liquid, gas, or plasma, have this type of solidity. Well, let me talk about entering the water. This gentleman's name is Jack, by the way. When one goes swimming, you don't actually enter the water, but rather push the water atoms apart to make space for your body. Well, what you state is true for most of your body, but water is a universal solvent that enters your skin. So to a small degree, if water enters us, it seems that we enter the water. But in general, you're correct, we push the water apart, and we don't often think of water soaking into our skin that way. Jack's main question is, does your model assume a fundamental solidity of particles at the lowest level, that is G3 or lower? Well, I'm going to talk about levels here for the moment. Philosophically, the lowest level is at infinity, and on that basis, that seems to be true, even though it's difficult to go all the way there and imagine how small something is at infinity. If it almost seems like it must be zero. Even though it seems philosophically true, I'm more pragmatic about it, and I stop at level 2 where there is some evidence. Level 3 is suggested by the model, not by evidence, and that makes it much more suspect. So the question is, how far down does it go? I deal with level 2 and suggest the possibility of 3, but don't do anything to try to support it or explain it and what it does. Okay, solidity. Here I am using solidity not to describe a state of matter, but to describe the near 100% elasticity of collisions between particles. In other words, to be elastic, you're compressible. Okay, G1 and N1 are called particles at level 1, but G2 particles must be able to pass through the G1 and the N1 in order to develop G2 gravity. The only way that this can happen is that the G1 is made up of atoms, in particular level 2 atoms. The structure of the atom is the only way to develop open space in a particle. Therefore, they are elastic and compressible, and they're not inelastic in any sense of the word. And how elastic and compressible are they? Talk about that a little bit in a moment. But solid is kind of a mysterious way to think of an atom, a particle that's made up of other atoms, which is primarily open space. So how solid is that? That would be my question back. Okay, he also talks about colliding particles. In an ideal case, inelastic particles can be considered perfectly round, and the resultant motion of the two particles that hit can be precisely described. So you do that in your early physics studies. When making mathematical calculations, this is what we have to assume. It's the only way we can use mathematics and describe colliding particles and what's happening before, what happens when they hit, and what happens after they hit. But for real particles, which can have odd shapes and are elastic, this ideal case is not necessarily valid and didn't spell necessarily right. Okay, his second question. So using your model, are G1s made of G2s, are made of G3s, are made of G4s, are made of GNs? And the G's are at any level and are always 100% elastic in their collisions if they collide with another particle. I answered the last half of that already. Or is there an imbalance of elasticity with collisions at different levels? Well, if G1s were made of G2s and G2s, then G2s could not pass through G1s. I'm suggesting that G1s are made up of level 2 atoms, atoms which have open space. All atoms are naturally elastic to some degree. Here's an interesting viewpoint. Level 2 gravity, which I claim is the nuclear binding force, atomic binding force, molecular binding force, is stronger than level 1 gravity, that is Newtonian gravity. Logically, the lower the level, the more inelastic, because the stronger the force pushing them together, making them more rigid, more solid. Third question, is there a collision hierarchy then? A G2 can pass through G1, but a G1 cannot pass through a G2, or put more broadly, a GN can pass through a GN-1, but a GN-1 cannot pass through a GN. Level 2 atoms are smaller than level 1 atoms. G2s can pass through G1s and N1s. Can G1s pass through G2s? Yes, but that's because the reverse is possible. G1s move slower than G2s. And if you visualize it, you got a slow G1 moving and you have a high-speed G2 moving, and it would appear that the G2 is swallowing the G1 is swallowing the G2, and then it sort of spits it out at the other end. But it's the other way around, that where G2s pass through the G1s, which is the normal way to think about it. G3s, if they exist, can act gravitationally with G2s and G1s. That's really an issue I haven't addressed at all, and I really don't know how. The dilemma is that the ratio of the forces caused by G3s on G1s, I have no information. There's no data available to ascertain that at all. But the fact is, the model would suggest that G3s will act gravitationally, not only with G2s, which I would suggest is normal in the model, but it also interacts with G1s because they're much smaller, much faster, and can act gravitationally What's the ratio of these interactions? I have no idea. The fourth question, is there enough evidence of anything being able to pass through an entire planet? I've read about gamma radiation being able to be shielded by a few feet of lead, though of course this only means it is reduced to a level that is safe. Surely the Earth with its thousands of feet of shielding can block all but a very few G1s. I know your numbers, 1000/990 in your example, are fictitious. Those are numbers I use with my circuit analysis. But it seems to me like the G1s passing through the Earth would be maybe 10, and the external unblocked ones would be 100,000, a much more larger ratio coming from the stars. Well, what he's saying is he doesn't think that they can pass through the Earth. Do we know anything about something passing through the Earth? Well, the standard model by mainstream physicists, they claim they know something that passes easily through the Earth, and that's the neutrino. The mass of the neutrino is much smaller than that of the other known elementary particles. So it's very, very small, like I'm suggesting the G2, for example, would be small like that. The weak force has a very short range. The gravitational interaction is extremely weak, and neutrinos, as leptons, do not participate in the strong interaction. Thus, this is the end of all this, thus neutrinos typically pass through normal matter unimpeded and undetected. Yeah, they're saying that it easily passes through and it probably doesn't hit anything. It doesn't hit and push. It doesn't get trapped. It does, they claim it passes through. If correct, maybe they are detecting the G2. If they did detect it, they may be detecting the G2 particle, not the G1, because the G1 is in the model is suggested that it's like the electron, which is one of the elementary particles, and the neutrino is smaller than that. More about the neutrino. In 1942, Gang Chang first proposed the use of beta capture to experimentally detect neutrinos. In the 20 July 1956 issue of Science, they published confirmation that they had detected the neutrino, a result that was rewarded almost 40 years later with the 1995 Nobel Prize. So they claimed in 56 they detected the neutrino, and the proposition is that it'll easily pass through anything unimpeded, undetected. Well, what about the G1? If the neutrino could be considered equivalent to the G2, what about the G1 passing through the Earth? That's my question. First, there is always open space. There's a lot of open space. Even with G1 passing through level 1 atoms, it's a lot of open. But second, G2 gravity is holding the Earth together and has an internal G2 gravity field inside. The internal G2 gravity field can guide the G1 through the Earth just like G1 gravity field guides an asteroid through our system, through our solar system, or our galaxy. The asteroid will just weave its way through, being guided, and only when it gets trapped or gets too close to an object will it collide and hit. So open space, and it will be guided through by G2 gravity, which helps it make it through the Earth. Okay, well, but there is no direct evidence of the G1 particle, and whether it passes all the way through the Earth, we don't know, because I'm just assuming that the G2 could be like the neutrino, but I'm not even sure the neutrino exists. Now, Newton observed the motion of the apple, the moon, and the planets and used that as indirect evidence for a force he called gravity. Yeah, we don't have direct evidence of gravity. We only have indirect evidence, and that's motion. Motion is direct evidence of motion, but Newton used it as indirect evidence for a force he called gravity. And until we have a detector that can see the G1, there will be no direct evidence that it even exists or whether or not it passes through the Earth. But here's an interesting point about your question, that maybe they don't make it through the Earth. Let's assume that none of the G1 particles make it all the way through the moon. That means the force on the surface of the moon will be the maximum force possible. Because if all of the ones are blocked coming through it, when it gets to the surface, you've got all the particles on the surface actively pushing down with no opposing force. And for that point in space, that's going to be the maximum force of gravity you can have. Well, that means that the force of gravity on the Earth would also be maximum. If it's blocked completely on the moon, it's going to be blocked completely on the Earth. And we know that the Earth has a gravity that is about 6 times greater than the moon. So the G1 conclusion, the G1 must pass through, or the particle model is wrong. As a matter of fact, when you read Lesage's statement about the model, his model, which is what this is taken from, this is one of the basic assumptions of the particle model. We assume it can go through. If it, first of all, does it exist? I just argued the point, we don't really know that the G1 particle, as I describe it, even exists. And then, if it does exist, can we show that it passes all the way through? But it's a basic assumption of the model, and we move forward using that assumption and see if it makes sense. And as it's been applied in many applications, I have been surprised as how many different ways and how many different applications the model, based on this assumption, seems to work. Here, the bottom line of the particle model is this is the whole issue finally. The only questions that can be answered using the particle model is this: does it give a better explanation than existing explanations? Yes, it does. We explain parallel resistors using it. We explain the double slit experiment. Or you can argue individual points about whether I'm making correct statements even based on the assumptions of the model. But the potential for explaining things that have not been explained by standard models is there. The second question, does it predict things that can be proved? Answer to that is my circuit experiment that I've done provided supporting evidence, not proof, for the particle model. The particle model predicts a certain behavior. I did a test, I measured it, and to a high percentage, my first test proved that prediction was valid. But without direct evidence, there is no proof. This is only supporting evidence. But generally, this is what happens. When you have enough supporting evidence for the model, it can be very compelling. You know, juries will be confused by eyewitness testimony, but when it comes to circumstantial evidence, and you get enough circumstantial evidence, that can be very compelling, and jurors have found people innocent or guilty based on circumstantial evidence. And if we get enough supporting evidence for the particle model, it can be compelling enough that maybe the model will get some interest. But only if it has a better explanation, and only if it can predict things that can be proved. Jack, thank you for your questions. That's the gentleman's name. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I explain more of the universe using the particle model. Thank you for your attention.